right, well, let's make, what's that?
I was gonna say, I've heard jokes where the phrase a square comes from, and it's just like, I don't know how true the actual explanation they gave you is or not.
Yeah,
It's
it's because
funny.
there's too many joke versions of it, that's
Yeah.
exactly right, so you don't know which one to believe. Yep. Anything you wanna talk about before we proceed?
How are the exams looking?
I have not looked at them, so I can't say.
Okay.
My personal rule is a week, and it's looking like I'm not gonna get to it till this weekend.
Mm-hmm.
And this weekend's gonna be tough, but I will get them done.
Mhm. Okay.
So I have no response to that. What else?
Mm-hmm.
How do you feel about it?
Cool. Decent.
Yeah, that's probably as good as anything at this point. Nothing else, so we're talking about this. Something goes to something else, goes to something else. And so the idea we had was an alpha particle, but we've done, we had talked about that as an alpha decay. We talked about this, and I can't remember exactly which ones I got. Which one's the X? There's an element up there that's just an X, right? That's an X alone. No, I'm pretty sure there has to be one that's just an X. No, I'm messing with you because I forgot the E when I wrote xenon. When I wrote it on the board, I forgot the xenon. So it was xenon, and I think those were all beta decays is what we talked about, right? Because in the case, A was the same for every single one of them.
Mm-hmm.
And the N's and Z's changed by one, so we figured out that had to be a beta decay.
Mm-hmm.
I'm writing this in terms of decay rates. That's what my equations are gonna be. In fact, I think in my notes, I'm really calling this 1, this 2, and 3. So thing 1, thing 2, and thing 3. That decays with gamma 1, that decays with gamma 2. And that's not what I gave you when I wrote it over here. I did not give you gamma. What did I give you? Do you bet?
The half-life.
Probably the half-life, right? It was definitely a time. And the most common way that people quote those, even though that it's not the most useful, it is the most common one is the half-life. How long does it take before half of thing 1 have changed to thing 2? How long before half of thing 2 changes to thing 3? We don't have that back reaction. Right? These are generally one way. In chemistry, you would have a detailed thermodynamic balance where you're going back and forth between those, and one would be more common than the other. But those nuclear decays generally only go one way. I mean, you can go the other way, they just typically don't. So, a useful exercise for you, you don't have to do it now, but I'll talk about it in a minute, so eventually we'll probably do it, is convert those times that I gave you, those half-lives, into gammas. And it's related to 1 over that time. A rate is 1 over that time, but it's not just 1 over that time. That was something I'd ask you guys to do. So, I think this is where we were. That's 2 down, right? Did I bring my box? I didn't bring my box. I'm not even gonna try. Because if I do get it in the right spot, it'll just bounce off when it hits the chicken bag.
They have a blue one.
What's that?
They have a blue one over there. I'm not sure.
Yeah, I'm gonna go. I'll go to those if the red one.
Yeah.
Yeah, the red was,
I read earlier today, I think it's fine. I think we just angle it so it stops putting ink up to the tip.
yeah.
Oh, is that right? Think it's just an operator error?
That's what I
Well,
noticed when
whenever
I was
I-
using it earlier. I don't know if it's run out in tons
Well,
since.
We'll try that here directly. So, dN1 dt equals minus gamma 1 N1. And that's kind of where we were. That's a macroscopic picture of the same random statistics that we talked about, except now we're looking at Avogadro's number of them. That means there's almost certainly going to be a bunch of them going off at any moment of time, and how many go off depends on how many are there, and So I can actually integrate that right away. I can separate those variables. Okay, now I'm ready to integrate. Who wants to do the right side? Go.
Negative gamma times T.
He assumed that this gamma doesn't depend on what time it is. It's independent of time. You almost always make that assumption. Keep that in the back of your mind that that is an assumption you're making.
Mhm.
Gamma comes out, now it's integral of dt, not so bad. Who wants to do the right side, left side?
Is that gonna be, the
Isn't
natural
it,
log of
isn't it
N1?
just n to the minus one dn? But I know how to integrate that, right? U to the n plus one over n plus one? Why
Yeah.
doesn't that work?
Cause you get,
Minus
Just
one
one.
plus one on the bottom. And that's not good.
yeah,
You're not allowed to divide by zero, right? It's just a rule. So no, I need to invent a new function. I have not yet.
natural log.
It is a natural
Yeah.
log, and I have not yet found out. I found when they invented the natural log, but I have not been able to discover who realized that the natural log they had already invented for other purposes was that. So I don't know.
Yeah.
I don't know who gets credit for that. But
They
this
just
is-
tell you to kinda like remember that in calculus.
Oh, yeah, yeah. It's the one that doesn't work for the power law. It's the
Yeah.
only one, right? So you need a new function for that. Okay, we're done, right?
Nope.
No, why not? What did we forget? What did at least one of you forget?
You get a constant.
Yeah, you gotta add a constant somewhere. You both didn't, so you're equally culpable. What is that constant? What's that gonna be?
Is it gonna be the initial amount?
Yeah, if I put in t equals 0, that's the log of n1 at t equals 0 equals c. And then when I do the algebra, I'm gonna erase that. Is that okay if I erase that? I then go back through and do the algebra. That becomes n1 of t equals n1 at t equals 0 e to the minus gamma t. So over some time scale, it will drop by 1 over e. That same time interval, another 1 over e, another 1 over e. So if I have a sample that's got some carbon-14 in it, and I know that it ought to have this much carbon-14, and it has exactly half as much carbon-14, what do I conclude? That it's been exactly 1/2 life since that carbon was buried under half a ton of garbage. So that's how you time things. Now, carbon-14 works for thousands of years because that's what its half-life is. A really, really small time, a small fraction of 1,000 years, not much is decayed, right? So it's not a really good way of seeing something that got buried just recently. If it's too long, if it's 100,000 years, well, all the carbon-14 is gone. It's really hard to see where the carbon-14 is, how much carbon-14 might have been there because it's all converted by now. So there's a window at which carbon-14 works to date stuff. Turned out to be really useful for human society, right? The last 10,000 years or so. It's kind of good for that. Doesn't take us back. But it turns out there's other stuff, right? You look around and there are other elements that have lives that are in the right time, and so you can almost pick what you want to use based on what time scale you're trying to look at. Now, it needs to be stuff that's in things, right? There may not be a lot of gadolinium in most, ancient animals or that kind of thing. There's definitely a lot of carbon, right? We're made out of carbon. But, so there you go. This is essentially the idea behind that. Now we're gonna do these other twos because that's one of the things that you check. We're gonna look at what happens when X goes to Y and when Y goes to Z, and so if you know that that's a radioactive decay path, you can check for how much of X is in left how much Y is in there now and how much Z is in there now. And by making those make sense, you can get a better idea for how long it's been since it was just X. So, but get the idea of what this is. They will talk about a little bit about dating, and I'm not going to spend that much time on it, but it might show up on the test, who knows. So that was not so bad. My next one is, I start off with only one, and so I have this certain initial amount of thing one, and it's going to decay in this way. I start off with no 2 and no 3, just because that makes my life a little bit easier. So if I start off with 0, 2, what's the only way I'm going to get some 2? What's the only way to get 2 from that, according to that reaction scheme that I've drawn there?
Do you have to wait
Wait
for a later time?
for 1 to turn into 2. So, how does N2 increase? It increases in that way. Does that make sense? Gamma 1 N1 tells me the rate at which I lose N1. Well, how do I lose N1s? They turn into 2s. So every time I lose a 1, I gain a 2. So there's an implicit plus sign there. So my 2s are going to go up as my 1s go down. And exactly, right? They don't get lost somehow. But what's the other thing that happens to 2s?
It decays to 3s.
Yeah, they turn into 3s. They turn into 3s. Son. At a rate proportional to how many 2s I have. So initially, you might look at that and realize, okay, initially it's just going to look like this one, except this is going to go up the way this one is going down. If I were to plot N1, N as a function of T, tell me what N1 looks like.
It's the curve.
It's that curvy thing. Yep, starts off with N1, 0, however much N1 I start with, and then that's just going to decay, because there's no mechanism in my reaction scheme to get them back, right? So they're just going to go away over some time scale. What is my N2 going to look like, at least initially? Well, initially, this is going to be 0.
It's gonna increase.
As in this, with the same slope that this goes down, it's going to go up. And then whatever happens, happens. We'll see that in a second. What's nice is that now I can solve this, though. I can put this there, and I have now only one variable. At the moment, I've got 2 variables, right? I got one equation with 2 unknown things in it. Well, one of them's not really unknown. I can solve that for this, put that there. Everybody see what I'm doing there? Because now I've got that. Okay, so I'm going to go ahead and do a lot of this in place just because I don't want to spread it all out. But when you need me to stop erasing things, tell me. But that's going to be gamma N1 0 e to the minus gamma t. In your differential equations class, they told you to rewrite that this way. That's the only time dependence. We just have the differential equations class. 1, 2. Okay, the rest of you are off the hook. What do they tell you to do with that? Integrating factor. What's a good strategy here? Integrating factor. It's a good way to go with it. Yeah, there's a part of that class when they said find an integrating factor. How did you know it worked? Because it was the chapter on integrating factors. Of course it worked in that chapter. How do you know it's going to work here? You don't. you just start rolling and you see if you can get to work, right? You go to all those differential equation solvey things that you were doing, figure out which one worked. And how do you know what if they're gonna work before you start? You don't. You just roll up your sleeves. So, but integrating factor works here. The integrating factor for this is e to the plus gamma 2 t. And if you've had the class, go back and remind yourself how you figured that out. If you haven't had the class, keep this in the back of your mind and you'll say, oh, of course I know that, I already did that. So, what that does for me is it shows me I multiply everything by that, so I'm gonna do that. That's what an integrating factor is. You multiply everything by that. So what have I accomplished with my integrating factor? People who've had differential equations. What does the integrating factor accomplish? What's the goal of it? How did you figure out how to get it?
I don't remember.
If you look at that, what do I have? An e to the plus gamma 2 on both of them. But look what I have. I have an e to the gamma 2t dn2 dt. Over here, I have an n2 dt times the derivative of e to the gamma 2t. That's really what I have here. This part is the derivative of e to the gamma 2t. Everybody see that? When I take the derivative of e to the gamma 2t, I get gamma 2 e to the gamma 2t. So what do I have here? First times the derivative of the second plus the second times the derivative of the first. What do I have? Product. Right. That's the purpose of an integrating factor, is to turn part of it into a product rule, into an exact derivative. What I have over here is the derivative with respect to time of e to the gamma 2t n2 of t equals constant e to the minus gamma 1 minus gamma 2 t. Can I integrate that? Yes, I can. Just multiply by dt. Who wants to do the left side? Me. Called it. Integral of a differential, what is it? That. Integral differential is just that. So that's what I get on the right side. Can I do this side? Well, the integrating factor technique works because over here I have a function only of t that I can probably integrate. Which I can. I can integrate this side, right? This is a function only of t, so I can integrate that side. I can integrate this side. I'm gonna write down what n2 turns out. What do y'all want me to erase? This side? Or do you want to see this still? Or do you want to just wait for a second? Take a deep breath. Bat her out. Okay. You can wait, you can't wait too long. So knowing what an integrating factor is and knowing how to get that, yes, that's outside of what we've done here. And if it seems, I have no idea where the heck that came from. Right, you don't see where that came from. But knowing that this is a product, that's in your wheelhouse. Knowing how to integrate this, that's in your wheelhouse. So a little bit in the middle there, but most of this should be able to follow. So I'm gonna keep those. All right, I'm gonna erase this over here. I'm just gonna do it. Integrated D is just gonna give me that. I'm gonna have that. E to the gamma 2 t n 2 of t equals gamma 1 n 0 and 1 0 e to the gamma 2 minus gamma 1 t over gamma 2 minus gamma 1 plus c. Figure out what c is. Tell me what you get for c. Think about it a little bit anyway. How do you evaluate c?
Put in 0.
Put in your initial conditions, right? I mean, that's not the only way to ever do it, but that's a good way to do it in this kind of problem. What's n2 at t equals 0? How much did we start with of n2?
0.
We assumed that we started with 0, that the only place we get to from is when 1 changes to it. So initially, there isn't any. So what do you get for c then? Tell me what you get.
So you get the negative of all that term.
Without this, right? Because t equals 0 makes this
That makes
1.
1. Mm-hmm.
So c is just there. If you put that in to the equation I just erased, here's what you get for n2. n2 of t, did it right? Gamma 1 over gamma 2 minus gamma 1, n1 at 0, onto e to the minus gamma 1t minus e to the minus gamma 2. We're going to look at these in a minute. I'm going to give you guys a couple of tasks. What would the equation for n3 look like? Tell me what to write down. If we assume the, go ahead.
Plus gamma 2 and 2.
There we go. The only way to get 3s, at least according to our scheme, is if a 2 changes into it. So whichever 2s I lose, they turn into 3s, and so that's what that looks like. And you could try, that kind of looks like this one up here, except it really isn't, is it? It's different.
Losing versus gaining. Like the
Okay,
negative.
okay, this is
positive.
losing 1s, this is gaining 2 3s, but it's different in another important way.
You don't start out with any of it.
Okay, I don't start out with any 3s, so it's different from n1, which I start out with some. Still also different in a kind of important way.
The T.
Gammas are different.
The gammas have a different value, but they're still constants, so they're not going to give me too much trouble. The t's, I mean, that's time, and so that started at the beginning when I had only 1s, and then went on for however long I need to before everything's over with. Still kind of different in an important way.
The n is increasing each time.
This is increasing and this is decreasing. That's true. I think we might have mentioned that. What does the rate of change of n1 depend on?
N1.
And what does the rate of change of n3 depend on?
And
N2.
N2, not n3, right?
Mm.
So this is not going to look like that. It's going to look different because the change in n3s depends on how many 2s I have. Well, how many 2s do I have? That's a weird competition between gaining them from 1's decay and losing them as 2's decay. If I don't start off with any 1s, I don't get any n2s. That kind of makes sense. What if gamma 1 and gamma 2 are the same?
You're gonna be getting them at the same rate you're losing them.
Yeah,
So that term is gonna be 0.
probably, but all I see is a 0 in the bottom. So you might have to, thinking from here, how to get gamma 2 and gamma 1 to be the same, you have to be a little careful about what things you're doing. Because if gamma 1 and gamma 2 is the same, this is 0 and that's 0. So what do you have? What do you gotta do with that? You got 0 over 0. What did they tell you to do?
Taylor series.
Go to the hospital. It eventually amounts to a Taylor series, but they said take derivatives of the top and the bottom.
Mm.
So you have to think a little carefully about how to do that, but that's what you would be doing here, right? You use L'Hopital's rule to see what is really going on with N2. Is it really 0? Every time you get one, do you immediately lose it? Or do they sort of bunch up, right? I don't know. I'm not sure what the answer to that question is. We're gonna do some of that, but we're gonna look at fast and slow rates. I didn't actually do those.
So you're saying you would use L'Hopital's rule to see if, or to see what that behaves like when
And your
R2
variable is
R1.
gamma 2 minus gamma 1, right? It's not x. But to see what this converges to as gamma 2 approaches gamma 1.
Okay.
Or as gamma 2 minus gamma 1 approaches 0. So you'd have to think a little bit about how that works. Here's where I would start. You don't have to do this if you don't want to. I'm not saying you won't show up on the test, but you're not gonna do it till the test shows up anyway. On to, and then if I factor that one out, 1 minus e to the minus gamma 2 minus gamma 1 t, e to the minus gamma 1 t. So now you can do a Taylor series expansion of this and figure out what happens if gamma 2 and gamma 1 are the same. So that amounts to also using L'Hopital's rule. So that's where I would start if I really wanted to answer that question. Make sure I did this algebra right before you spend any time on it. All I did is factor out this e to the minus gamma 1t. That left me 1 there, 1 minus, but hopefully I did the rest of it right. I did it all in my head, and that's never a good idea. Okay, so I want you to spend a little time thinking physically about what's going on there, seeing if that makes sense. In particular, consider not this case where gamma 2 and gamma 1 are close to the same, but when one's really fast compared to the other. Right? If it's really fast to convert this and really slow to convert that, you can sort of think physically about what the consequences of that would be. See if this is telling you that. See if your physical intuition matches what the math is telling you ought to be true. Find N3. Here's the answer. Again, some weirdness if gamma 2 and gamma 1 happen to be the same. Also an interesting question is to ask yourself, what happens? I'll give you guys a second, but I'm going to erase all that because we're going to look at again, if one rate is fast compared to the other, and then think about what that means physically. Take a deep breath. Bat her out. All right? Questions? Yeah. Nope. then what if gamma 1, I'll erase a lot of this. I'm probably gonna have to rewrite some of this back. Almost all of this I'm gonna have to rewrite. What if gamma 1 is much, much bigger than gamma 2? I'm gonna do all that, and you can imagine that when I get done here, I'm gonna tell you to consider the other extreme, that gamma 2 is much, much bigger. Physically, what's going on there? Gamma 1 is really, really big number compared to gamma 2. What is gamma? What are those gammas telling you?
That's how long
Decay
it
rate.
takes to decay.
There's a rate, it's a short time. If you have a big rate, that means it's a short time. So what happens physically? What's happening?
X's are decaying very quickly.
The
and then-
2s?
Yeah, and then the 2s are decaying very slowly.
Yeah, so what do you expect? What do we think ought to be true at the end here? How many what should N1, N2, and N3 look like?
Probably gonna have more Y than X.
Yeah, probably we expect this number to be small, we expect that number to be big, and then, you know, this number to be growing as that.
Yeah.
The gamma 1, we can speculate that the gamma 1 won't be in there. Because the gamma 1 tells me that these are all gone. And now it's really just Y changing to Z. Again, speculation, let's see if the math tells us that. So N2, gamma 1 over gamma 2 minus gamma 1, N1 at 0, e to the minus gamma 1 t minus e to the minus gamma 2. If this is a really big number, this is an e to a big number, this will be small compared to that. This would be small compared to that. I don't know what I just said, but that's what I meant to say. Big number, e to the minus big number, small number. So this will be approximately gamma 1 divided by small number minus a big number. At least initially I can write that as just that big number. N1 at 0 on to 0 minus that number. So in this regime, in gamma 1 big, x's change really fast to y's, 1's change really fast to 2's. Does that seem a reasonable result that N2 of t, because that's what this is, looks like however much N1 I started with, e to the minus gamma 2t? What does this look like? This looks like I started off with this much N2 and it just decayed to N3s, right? Isn't that, because that's what we got before. The decay of 1 to 2 was N1 naught e to the minus gamma 1t. But now N2 is however much N1 I started with, e to the minus gamma 2t. Does that seem reasonable? How does that seem to make sense physically? Nodding your head.
You're losing X very fast.
Yeah,
Yes.
the x's are gone, right? The 1's are gone. How much N2 do I have? All my 1's are now 2's. What do my 2's do? They decay with this rate into 3's. In this term, well, I don't know how to have it. Look at the differential equation that I started with and ask yourself, what does that look like if gamma 1's really fast compared to gamma 2? N3 is approximately the best way to do that. There's a lot of algebra here, but I'll just do it. To start off with, I'll just write down what I had before, and then I'm going to change it in place. N1, 0, on 2, 1 minus gamma 2 e to the minus gamma 1 t minus gamma 1 e to the minus gamma 2 t over gamma 2 minus gamma 1. Where are we? Gamma 1 really, really big. So this is approximately, I've got an N1 0 in front, 1 minus. Tell me what to do with that stuff inside.
Gamma 2 times e to the minus r1, or gamma 1t just becomes very close to 0, right?
Yeah. So your idea is that gamma 1 big over a comparatively short period of time, this will suppress that term. So let's see what happens. Get gamma 1 minus gamma 1 is gamma 2t
Over negative gamma 1.
Who wants to do the first part? What goes inside the brackets?
1 minus.
There we go. That's good enough. She did her part. Next. Go ahead.
E to the negative 2 gamma t.
Gamma 2, yeah, gamma 2t. Anything else?
Nope.
Does that make sense? Let's see if we can make it make sense. N3 of t equals N1 0 times 1. What do I get when I do N1 0 times 1?
And
N1
Very good. N1 0 minus, what do I get when I multiply N1 0 times e to the minus gamma 2t?
You get n2t.
Boom. So does that make sense? That the N3s are whatever I started with minus however many N2s I have at any given moment. And ultimately, those 2's are going to change. If I were to plot this, I start off with essentially N1 number of N2s. My N2s start off with however much 1 I started with, because they change right away. So they started here, and it goes down exponentially. That's my N2. What does my N3 do? Does the same thing, except it starts at 0. It's almost like I only have 2 species, right? This is like a 2 species decay. because the ones changed long before I even came on the scene. And now now all I have is 2's turning into 3s. So hopefully you have a feel for what you're gonna expect when you do exactly the same thing except reverse that direction. Now gamma 1 is really, really small compared to gamma 2. Physically, what's going on up here? If I make gamma 1 tiny compared to gamma 2,
X is slowly decaying into
yep,
Y.
they really slowly change to Y's and then,
Y very quickly turns to Z.
right. So what do you expect? What is that almost certainly gonna look like when you get done writing all your equations? You're gonna do the hard part and you're gonna do the approximations, but you're gonna get to what ought it to look like.
It's gonna look like X straight to Z.
So slowly, quickly, yes, I agree with that. I was thinking just that, but you're right. Those are eventually gonna go, yes. It's almost like the Y doesn't really matter. So that's that sort of decay idea. We talked about beta decay a little bit, and I'm going to talk about it some more. We've talked about spontaneous decays. I mean, I guess that's the way to think about it. We talked about things breaking down spontaneously to others, and that's kind of why they only go in one direction, because they're endothermic, they release energy, and that's the ones that go naturally. Eventually, we're going to talk about inducing those reactions. So it turns out a lot of those won't go unless you hit it with a neutron. And if you hit it with a neutron, it will go. And then that's, rather than a decay, you would call that a reaction. That's where you have stuff on the side and you make stuff happen and you form your product. We talked about beta decay. I'm going to draw this picture and you tell me why it's relevant. What am I drawing? Obviously, you would have no idea out there on the street, but in this class, given the context, what is that looking like?
Forgot what it's called, the shell energy levels.
Those are the energy levels, exactly right, yeah. The shell model was a little beyond that, but that's how we get, no, but we start here and then we build. What's relevant here, why is this relevant to the symmetry term? And why does it get us ready to talk about beta decay? That picture. Why does that picture lead into beta decay? How does it explain the symmetry term? Just to remind you, the symmetry term looked like this. It might not be A down below, I'm not really sure. There was something on the bottom, I just don't remember if it was exactly A or if A to the 4th, 7th power or something ridiculous like that.
It had A under the n minus z squared.
Okay, but it was A?
Mm-hmm.
Okay, so whether I divide it and then multiply or multiply
Right.
and then divide, that. So I did it, I remembered it right. That's not quite so minor difference. What did the symmetry term purport to do? What was it supposed to accomplish? How did it help us? Why did we jam it in there? We had no good reason except one to put it in there. What was
it
the reason for
pairing of nucleons?
Wasn't pairing yet. There's another pairing term that's a separate idea.
You want a similar number of neutrons. and
Look at the
protons.
table, right? You look at the table, and everything up to that point said there shouldn't be any protons. No protons, right? Protons just screw it up. One proton, right? But you put two of them together, you know what they're like. Right? Two protons together messes up the energy. No reason to have them, given the terms that we had up to that point. How did we finally understand that? How many protons how many neutrons, we'll start with the neutrons. How many neutrons can I put here? 2? Because I can put 2 neutrons in the same state, right? No, why can I not do that?
Because they're identical particles.
And they're also fermions. Turns out the bosons are also identical and indistinguishable, but they get to all be in the same state. They behave differently. But they're fermions. For whatever reason, fermions also have spin 1/2. I don't know if anybody understands that yet. I certainly do not. So they're spin 1/2 particles, and that means 1 to a customer. Each one goes into one state. Well, how do I get away with having 2 there?
Opposite
Spin up,
spins.
spin
There
down.
you go. They are in different states. They're in the same energy state, but they're in different spin states. All right, so there's my 2 neutrons. Now I put in 2 more, because that's what my model up to this says I ought to do. What does this say I better do? This says that's costs energy. That raises the energy. What does this say I ought to do? When does this cost me 0?
N and Z are equal.
And N and Z are the same, right? Are N and Z the same there?
Nope.
This is N, number of neutrons, this is Z, number of protons. Clearly not, right? And we can see why it's raising the energy, because they're in the next energy state. If I try to do that, those will just change. Why doesn't this Coulomb energy screw this up? It's too small. It's there. It definitely raises these energies a little bit because the proton states have that repulsion, but it's so peaked compared to these nuclear forces that are in there that to first order you can dump it, and we're going to do that when I write some equations. The first thing we're going to do is we're going to throw out the Coulomb term. It's just not big enough to stress over. If you're going to build a nuclear device, yes, you have to worry about it. But in terms of what's really going on, the physics that's going on in there, not relevant. So we'll see that. We'll see the numbers on that. So how do I change a neutron to a proton plus an electron? What force does that?
Weak nuclear
Weak
force.
nuclear force. That's exactly. Why did I put the word force in quotes?
It's not really a force.
Doesn't have anything to do with what you think of when you think of a force. When you think of gravity, pulls things together. When you think of electric and magnetic forces, makes things turn, changes their velocity, right? Causes an acceleration, just like you used to. Even the nuclear force kind of does that. We don't really understand it as well as we do some of the others, but it holds things together, right? You gotta pull them apart. You gotta do work against that force just like you're used to. Weak force is the only one that's not. It's really not a good name. Interaction works. But this is really all it does. It tells you how that happens, how you change that. Charge is conserved. What else is conserved when I do that?
Mass.
What's that?
Mass.
Mass and energy. Yeah, I gotta worry about that equals MC squared business. So some of that, if I were to add these masses, I don't get the same number as this. It's a little bit different, but we're kind of used to that, right? That happened all up and down the table. What else?
What else did you say was conserved?
I didn't, I asked you. What's
Charge.
conserved in there? Charge is conserved. Did I say charge is conserved?
I thought you said,
Well, maybe I did. Maybe. Gave it away, son of. Yes, no charge, no net charge, right? Charge is conserved. What else? How many baryons do I have on the left? What's a baryon? Bary means heavy. So a baryon is a heavy particle. Which of those particles up there are heavy?
The proton.
Yeah, and the neutron. They're both equally heavy, right? Almost. They're not quite identical, but they're pretty close. That's a baryon and that's a baryon. What would you call that, since it's not particularly heavy? A lepton. Lep means light. That's a light particle. So baryon number is conserved, but not lepton number, because we got a lepton on the right, but not on the left. Turns out if you carefully look at all the energy, some of it's missing. Some of the energy and momentum is missing. So energy and momentum are not really conserved. At least not here. You guys gave that up so easy. Energy momentum conservation? Oh my God, we need that so much. But they were doing these experiments and they were measuring that, and they found out, yeah, I can calculate the masses. I know where all the equals mc squared energy is. I can measure the speed of all these, right? They had a cloud chamber. They put a cloud chamber in there and they watched those things moving, and they were able to figure out their speeds if they knew the mass. So they knew the kinetic energy of everybody. Missing. Kinetic energy and momentum was missing. There were people who said, like you, hey, you know, whatever. It happens, right? Energy's conserved except when it's not. Momentum's conserved except when it's not. Wolfgang Pauli said, nope. There's still, it's in there, you just gotta go look for it. And so they eventually found an anti-electron neutrino. And you have to write this down because we're gonna talk about this a lot more later on in the semester. He told them to go find this thing that's virtually impossible to see. They would never ever have found this except for the belief that energy and momentum must be conserved. So that's why we really believe in energy and momentum conservation. Because it looked like it wasn't conserved, and everybody was a little nervous about that. And they said, this is what the properties ought to be, go look for them. And there's a movie about the sun going out. Anybody heard of that one? So they were looking for these because this should happen. When I take 4 protons and glom them together, that's helium, right? Not helium, is it, right? What is it? It's beryllium-4, right? It's beryllium with no neutrons. That's what I made. No, it's not what I made. I made, whatever that is. If you got 0 protons, what element are you? I don't know, probably nothing. What's that?
a neutron
There's a
star.
word for it.
Yeah, oh, there you go, you're a neutron star, just a tiny, tiny little neutron star. That's what I made. I made a itty bitty little neutron star. This is beryllium-4, right? 4 protons, nothing else. How do I get this energy down? How do I reduce that energy? That's too much energy. How do I get it down?
Protons become neutrons.
Yeah, I gotta go this way, right? Gotta go that way. And that's what happens. Now now what is it? Now it's helium. So what I talked about, 4 protons glomming together, that's what happens in the sun. It happens down in the middle. But they've got to convert, and when they do that, they make these neutrinos. And we're sitting at Earth, and we measured those neutrinos, and there weren't enough. We got much fewer than there should be, given how bright the sun is. And that one of the speculations was the sun had gone out. We just didn't know it yet. Because if it goes out in the middle, right, it can take tens, hundreds, thousands of years, hundreds of thousands of years before you even notice. That's how long it takes that energy to percolate out from the center. They figured
So-
that's not it, just so you know. Whatever happens in the next 100,000 years is not going to be the sun going out.
So you said in the center of the sun, you'll get 4 protons sticking together.
Yeah, called the proton-proton interaction, and it doesn't glom all four together, right? They basically glom together and
Mhm.
make deuterium, and it's a complicated process, but
And you said,
the gist of it is you effectively take four protons,
mhm,
put them together, two of them decay by beta decay into neutrons, and then you have helium, which is what I do there.
and they decay by absorbing an electron and a neutrino?
Well, I'm getting a little ahead of myself here, but I can add positron, and I can add an electron neutrino to both sides. And I have to add them to both sides. So mathematically, those two cancel, because they're inky particles. And so how does a proton decay? It goes to a neutron plus a positron, just like an electron, it's got positive charge, plus an electron neutrino. And all the same things get conserved. Positive charge, one baryon, one lepton, a lepton and an anti-lepton, so those cancel, the lepton number cancels. We'll do those later on in the semester.
Okay.
I'm kind of getting ahead of the game, but what I'm trying to do right now is get to how this happens, right? It has to do with this symmetry term, beta decay being the mechanism by which a neutron star converts into these, right? My tiny little neutron star converts to helium,
Mhm.
or my beryllium-4 converts to that. I guess, keep in mind that a neutron by its lonesome can decay into a proton, because the energy on the right side is the same as the energy on the left side. A proton by its lonesome can't decay to a neutron because it would have to raise the energy. If you look at that carefully, the neutron is a little bit more massive than the proton.
Mhm.
And so what happens is there's not enough energy in that process. If there are a bunch of them together, it can happen because it borrows some of the energy from somebody else. So your beryllium-4 can decay to helium because the remaining protons provide some of that energy that the protons use to convert. So a beta particle is like an electron, except a beta particle comes from a nuclear reaction. An electron is just an electron, but if it comes from a beta decay, you call it a beta particle, but only then. Gamma decay is one of the ones we're going to talk about. If you look at gamma rays have the same frequency as X-rays. And so the difference between them is where they come from. Gamma rays come from a nucleus, X-rays come from electron states in an atom. They're just really, really high energy. We'll talk more about this when we get to those. We have done a lot of this before. I'm just going to recap a bit of it. So all I'm doing is rewriting the semi-empirical mass formula. Notice that pairing term is different between the two books. I haven't actually looked carefully enough to see what the state of knowledge is on those. I also did spend a little time messing around trying to get that fit to A. I never did get there to 1/3. I even just said, just plot it A to the 1/3 and see what you get. It's close, but no cigar. So I think there's a little bit of aspirational thinking as far as getting that model to work on that data. But in any event, this is my M as a function of Z. We also talked about how do I find the most stable configuration, and how did we decide to do that? We looked at a minimum energy, because that's what the stable configuration is, right? Minimum energy. How do I find the minimum of that function? With the Italian calculus.
Take the derivative, find the derivative at 0.
Exactly. Take the slope, find where the slope is 0, and that's your bottom. Double check, you want to take the second derivative, make sure it's concave up so you know you're at a minimum. We did all that, right? Everybody remember that, even vaguely? Yeah, we did all that, so I'm going to write some of the gist of that. But I will say a few things. A couple of things. You have a fixed term. When I take a derivative with respect to Z, constant, constant, not even there, not there, 2Z, so that'll be Z dependent. That'll be Z dependent. That's gone, although we're going to come back to that. But that does not depend on Z. So where are my Z dependent terms? They're there. Those are going to show up as a Z dependence. So they will vary and cause Z to get bigger. It turns out this one's going to be small enough I don't even care about it. That we did that before. It was like, man, it's like carrying a 0.72 all the way through, right? And again, if you're going to build a nuclear reactor, then yeah, you worry about it. But in terms of the fundamental physics of what's going on, Coulomb term essentially doesn't matter. So what matters? You have this fixed term, and these Z-dependent terms. It's the competition between those that matters. That gets you to that minimum. And so we did that. dm dz turned out to be, there was the mass of the proton plus the mass of the electron minus the mass of the neutron. So that's like the energy difference between those. That turns out to be pretty small in the grand scheme of things, mostly because P and N are about the same. Minus a Coulomb over a to the 1/3 c squared minus 4 asymmetric over c squared. And that's really the important part. This last one is really the one that matters. Plus 2a Coulomb over a to the 1/3 c squared. That's a 3. Plus 8 asymmetry over a c squared z. set that equal to 0, and you wind up with, and again, this should look familiar. Set that equal to 0. Solve for z, that's z minimum. So the Coulomb term on the top, I got rid of. That was here. I keep it here. This is also the Coulomb term, but it goes like a to the 2/3. And so it turns out for a big enough, it starts to matter. And again, this is just recapping what we did before, but if a is small enough, that says that z, the z which gives you the lowest energy, the most tightly bound system, is when z is a times 93.6 over 185.6, and that's about a half. That's 90 over 180, that's about a half. And if you look at that table up there, that's what you see. You see on the upper part of the table where a is not so big, you see about as many protons as neutrons. As a gets bigger and bigger and bigger, the denominator gets bigger, and z is then less than half of a. And so you look at that picture and you see that's exactly what you see up there. As you go down the table, you get more and more neutrons for a given number of protons. Disproportionately many neutrons. And that's additional nuclear force to compensate for that electrical repulsion that those extra protons are adding. You only get nuclear force paired on pair. The Coulomb repulsion, they all repel each other equally. Every proton repels every other proton, whereas they only bond to nearby nucleons. Did I tell you guys to do mercury? Because I did A equal 135. Yeah, so I did 130, where you at? A is 135. And that could be tellurium. Where's tellurium? TE.
52.
There you go. Tellurium 52. That, if it has an A of 135, is not that, right? That's 127. So that's many more neutrons than the average, according to that. It's got a half-life of 19 seconds. So what does that tell us? It really is not stable, right? What about iodine 53? Again, not 135. It's got a lifetime of 6 hours. Xenon 135 has a lifetime of 9 hours. You see it's getting longer. Cesium 132, getting close, getting warmer. A lifetime of 2.3 million years. So as far as we're concerned, that's stable enough. But as far as the universe is concerned, not good enough, not nearly good enough. Barium 56, that's past, right? That's 137, but again, close. That actually is stable, but it's only 6.6% of barium. So it's a small fraction of the barium. Most of the barium is apparently 137. And then once I get past that, I go lanthanum and cerium. Where are those? Lanthanum is right there. CE 58.
It's in that block.
On the second.
Oh, that's such a pain in the ass. Yes, so lanthanum is 57. It's got a 20-hour half-life, as does cerium 58. It's got about an 18-hour lifetime. So as I go away from that minimum 56, 57 barium, as I go to the left or right of it, it becomes less and less stable. So if I were to draw, and then in my notes here I say do the same thing for mercury 200. So mercury 80, 200, right? Do the same kind of calculation. So mercury has 80 protons, so you should go either side of that, but look for the lifetimes of the 200, A equal 200. So that will be gold, but gold with an extra 3 neutrons, I guess, to get it up to 200. I'm kind of doing that in my head. I found, like for example, polonium-84 has a 15-minute decay half-life. So where's polonium? Polonium's over there at 84. It's normally got 209, and so it's neutron poor, I guess you'd call it. It has fewer neutrons than it needs. Do the same thing except for that 200. What we're going to do next is, so that's sort of one parabola, right? Basically, you're moving up and down the parabola. Give me 1 second. He's got a nice picture of that in here. You look at page 31, like 4.3 beta stability. That's the kind of thing we're talking about.
Is it
Even
the
better,
same?
even better. Yep, even better. So that's one species.
Mhm.
This is going back and forth if you add the pairing. So far, what we've been kind of talking about is without the pairing term. And so now we're going to throw in the pairing term, and that gives us 2 parabolas offset, and you go back and forth between those 2 parabolas. So we'll talk about that. That's our next move. So figure 4.3 gets you ready. That's what we've been talking about, figure 4.4 and 4.5, or if you want to tell everybody what those are.
16.7 and 16.8.
And
from
that gets you,
iceberg.
yeah, that gets you ready for what we're going to talk about next time.